today on case studies, and in particular, certain rivers which provide us with some information or opportunities to learn some lessons. Okay, so these are the ones we're going to be looking at, and let's begin with the Black Hills. And this is an example of what we call flash flood. It is a intense amount of rainfall in a nearby area causing a very rapid rise, 15 inches in 6 hours. Large numbers of people killed and displaced, and a large amount of damage at the time. Now, when you look at the isoplex map of rainfall, you see that there were very large areas of over 14 inches, and they're all coming down the Black Hills, down towards a series of cities that are built at the foothill, at the foot of the Black Hills. So these are the hydrographs at various places. This particular hydrograph, it's a discharge hydrograph, shows how quickly the water rose in just a few hours. Literally in about 3 hours, it went from almost, let's say, 2,000 cubic feet per second to 50,000 cubic feet per second. Okay. Now, as far as the elevation, it went from less than 2 feet to almost 16 feet. And again, within just a few hours. So this type of flooding is particularly difficult to deal with in terms of evacuations, because you have such a small amount of time between the rainfall event and the peak discharge. Okay. Now, it was a big flood. At one point, it was estimated as being a 500-year flood. Later work suggests maybe it was more recent than that, and one of the themes we'll end up with talking about flooding in the Houston area is that what we used to think was the 500-year flood is probably much more common than we think. So how do you deal with something like this? Well, there was both a tragedy and an opportunity here. It wiped out a large part of Rapid City along the floodplain. And so it allowed the planners and politicians to develop what they call the Greenway concepts. And so this is really the takeaway for this particular flood. Most of the floodplain was converted to parks. The businesses that were allowed to stay in the floodplain had to flood-proof themselves. And what that usually means is raising it to be above the flood level. And whatever houses and or motels that were there were either moved outside the floodplain or were simply leveled. And the underlying concept was that nobody should sleep within the floodplain. So it focused on the allowable uses in the floodplain, thereby eliminating a lot of the risk with respect to these sudden floods. Okay. In 76, there was a similar kind of flood, but here, again, a lot of rain falling, in this particular case in the Rockies, hundreds of people killed, thousands injured. Again, a large amount of damage. When we look at that particular flood, Brent, there were basically orographic rising of the air that was humid. It fell, and it fell basically at the head of a canyon. This is the Big Thompson Canyon. Okay, and so here again we have this kind of a linear rainfall, 10 inches here, and it's going down the canyons again. Now, in the case of the first area, what the people that died and the issues were essentially the city at the foot here. Here, it was the people that, this is just comparing it with Rapid City. Here, though, instead of Rapid City being destroyed, it was small populations within the canyon itself. So this is one of those narrow, steep canyons where you had a series of little motels and homes. You can see some of them here that were just literally wiped out. as this flood came by. And again, because this is a flash flood, there was almost no warning. Okay, so there's two things that came out of this. Again, the lessons learned. And perhaps the most important was an early flash flood warning system. And in some cases, it's quite simply climbed to higher ground. Because quite literally, the difference between life and death could be standing here or standing over there in these flash floods as this wall of water comes down. But the other thing that came out of this was that as people began to look at this, they realized we didn't have a long history of flood records in these canyons. And so is there any other way that we could try to figure out the frequency of these things in order to establish some question of risk involved? And the answer, was looking at paleo floods. So we're going to look at how you can use the, if you like, the botanical and geological record of floods to try to reconstruct their history. Now, in terms of the warning system, you have a storm event. And notice this is about a 3-hour period. You don't have much time. And the storm is developing, and the rain starts to fall with a peak here. Okay. Well, there's a detection system that's monitoring the rain. Okay, that's relatively easy. But then, within a half hour of heavy rain in the headwaters, there's a public safety mobilization where essentially the county is putting together to see if there's going to be a potential peak flood. Warnings are issued and the public responds. So that within an hour or so of the peak rainfall, you have people evacuating. So this is the system. And it should remind you a little bit of the Lahar warning system, where you're monitoring these events because if you wait for them to happen, you just don't have time to get out of the way. Okay. Now, with paleo floods, what do you look for? In this particular example, you look for things like erosional niches, broken trees, scour. Well, that will tell you where the floodwaters were. In fact, I think I've got one here. This is a flood on the Blanco River, and you can pretty much determine where the maximum stage was by where the broken trees were. Here, what you're looking at is the scoured on the tree versus where the trees are untouched. The debris lines, debris was up there. So this was a pretty massive flood. And again, it was a peak flood. It rose and fell in just a few hours. So now we know the stage, but that doesn't tell us the recurrence interval. So we need to figure out what is the age of that flood, what is the age of the stripping of the bark. And the good news there is that we can use dendrochronology. We can look at tree rings and determine when were these trees broken, when were these trees killed. Okay, so that's the first thing. Botanical evidence to determine both how high the flood was, the stage, and also the age. And of course, if we know the magnitude and the event, then like earthquakes, we can begin to put together the extreme event recurrence intervals. Now, the other thing, though, is that we can look at sediment that's deposited by a stream. Now, in a flood, the flood deposits don't always tell you how high the water was. They simply said there was a flood. There is an exception, though, and that's what they call slack water deposits. And let's just imagine here's a big stream stream that's being flooded. Here's the high water mark, and let's say you got the high water mark from debris lines or broken trees, etc. When a tributary rises due to a peak stage or flood stage, when a main stream rises, the tributaries begin to flood, and the waters begin to flood into the tributaries. They literally back flood. And so what that does is you've got a big river coming down, there's a tributary coming around. Well, some of that flood water spills into the lower part of the tributary. And so it'll often deposit what are called slack water deposits. And those deposits can be close to the high mark. In any case, they're deposited in sheltered areas. So it's not uncommon for a little alcove, little recessed areas to see these deposits. And so these slack water deposits, here's one in an alcove in limestone deposits. Here's a series of them. This is just some examples of these deposits that are storm deposits. You can develop their stratigraphy. So you got flood deposit, and then notice it says colluvium. Colluvium is just stuff that comes down by gravity. It's the slope wash. And then flood deposit, slope wash. Flood deposit, slope wash. So we have this stratigraphy that is a record in these tributaries, in these slack water deposits of old floods. And if you can use radiocarbon dating, we now have some newer techniques of dating, then you can, again, work out the chronology and use it to determine the flood frequency. This is an example where you're looking at floods going back to 360 BC, 160 BC, up to 612 AD, etc. It's kind of odd to be using those numbers we usually use before the present. And just as an aside, before the present means before 1950. So we're not constantly having to revise it as we get farther and farther away. Okay. So again, these are the radiocarbon dates. On charcoal, these are dates on seeds. And so that's how we go about reconstructing that. Now, looking at these outliers, and an outlier is where you have a really unusually large event. And so what you'd like to do is figure out, well, was that event a 90-year event, because that's how many years of record we have, or was it an unusual event that probably occurred over here? And so we just happen to have it. And so that gets into the question of how do we extrapolate our flood frequency diagrams to the really large flood. Okay. Well, when you begin to look at those paleo floods, you get a much better idea of filling in the gaps. And so it allows you to kind of see where the 1972 flood occurred. So now what we have historical records in black, and that one really big flood in 1972. And then in here, we have these slack water deposits that allow us to fill in the gap. And it turns out it probably wasn't a 500-year flood. It was about a 200-year flood based on more data. Okay. Those were all flash floods. They're very different than regional flooding, such as happened in 1993 and even before then in 1927 along the Mississippi River. In 1993, you had a very large amount of rain falling in the upper part of the watershed up into Missouri in the area for months. And locally, it was a 500-year flood. Okay. But notice, 48 people killed. These really big floods tend not to kill many people. And the reason, of course, is the time of concentration, the time it takes for that water to come down is larger with bigger watersheds. And so you have the ability to evacuate. On the other hand, the damage of these really big floods is much greater because of how much of areas can be destroyed. For example, in that Great Flood of 1993, $20 billion, 50,000 homes were destroyed. Now, one of the things to note with this particular flood is that perhaps most of the damage was associated with failure of levees. And when you look at the levees, it turns out that everybody and his brother can build a levee. Now, there are federal levees that are built by the Corps of Engineers. but there's also county levies and subdivision levies and town levies. 3/4 of those non-federal levies failed, and less than 10% of the federal levies failed. So one of the problems is we think that we're safe because there's a levee between us and the river. And so we build on a floodplain, except that not all levees are built the same. The event itself was, again, regional. You looked at long-term air patterns where you had the jet stream stalled and giving a huge amount of rain in the upper part of the Mississippi drainage. Here's a Landsat image of the Mississippi River before the flooding, and here it is during the flooding. And this is the hydrograph. Now, again, this is a discharge hydrograph. This is in thousands of feet per second. So we went from about 400,000 to 1,000,000 cubic feet per second. And notice we're looking at a lag time of 30 or 40 days between the inception of flooding and the peak floods. You might notice there's a little decrease here, and that's kind of an interesting thing. You normally don't think of floods rising and then all of a sudden decreasing and rising. That was associated with levee breaks. Now you might ask yourself, why would a levee break cause the level of flooding to drop? And basically when a levee breaks, it takes some of that water and parks it on the floodplain. So there is a drop until it gets caught up again. And so you had discharges along the upper Mississippi that were larger than normal, literally for months. And this is, again, just an example of how widespread the flooding was on the floodplain. This is 10 kilometers for scale. Okay. Again, this is the hydrograph, and turns out that this isn't the first time we've had really big floods. The red is in 1993, but there was a really big flood back in 1973, and another pretty big flood in 1965. So these are not unusual events in the greater scheme of things. Okay, so we had this little article in the paper talking about this town. Every time the river jumps, every year it overfloods at least once. In 1977, so bad the town was submerged. The town moved. So that certainly is one thing you can do. We saw it in Pakistan. We saw it in other areas. Sometimes it just isn't worth the damage that you're getting. And as we'll see with respect to floodplain insurance, we're seeing more and more that it makes sense to simply have people move than to pay to repair the houses. So we'll talk more about that probably next time. Okay. Mississippi River has a huge drainage area, and so again, this is just looking at the areas that were flooded in the 93 flood. Okay. This is a before picture, and that's an after picture. So you can see that there are just an awful lot of area, including urban areas as well as agricultural areas that suffered. So what are lessons learned? Okay. Well, I just forgot to put it on, but I'll tell you one thing, and that is that bigger floods with larger drainage areas, sometimes they're called upstream floods, I'm not quite sure why, tend to cause less loss of life, but much greater economic damage. The other thing is that much of the flooding is exacerbated by levee failures, or better said, much of the economic damage is exacerbated by the failure of levees. Okay. Now we're going to come back to another flood on the Mississippi a little later, and this is the 1927 flood. And some of the results of that flood were really quite interesting, but I want you to keep this flood in mind when we come back to it. Let's look at a different river. This is Grand Forks, North Carolina. The entire town is flooded, okay? And it's flooded to some fairly high amount. The area then caught fire, and of course they couldn't put it out. So there's this irony that you've got buildings that are engulfed in flames while surrounded by water. But it was a disastrous flood in 1997, and this was along the Red River. It's the Red River to the north. And this river is kind of unusual for a couple of reasons, but one is it floods to the north towards Canada and Hudson Bay. Well, it was not a flash flood, so we could evacuate people. In fact, 80,000 people were evacuated. It was the largest evacuation since the Civil War, but there were only 5 people that died. So again, economic loss, greater than $5 billion. Lots of damage, few deaths, okay. A lot of evacuation. Think again, you could imagine Mount Pinatubo. Remember how our ability to predict and evacuate saved so many lives in that event. The cause is kind of interesting, and that is that there was a record snowfall, a quick thaw, and then a blizzard. And so here was a case where the mechanism for the flooding was basically snowmelt, as opposed to the mechanisms we saw earlier and anything we would see down here. The water rose up to 54 feet. It was up to 26 feet above flood stage. It created a lake 25 miles wide. Now that seems odd until you realize this kind of the geologic setting of this area. Okay, here's the river heading to the north. Okay, and this is the extent of flooding. I can't quite read where Fargo is, but it's down here someplace. We're up into Canada here at Winnipeg. Notice Winnipeg didn't get flooded, and that is because Winnipeg had a large river wall and a diversion dike that took that water, and instead of having it flow through the city, it basically took it off to one side. So there are things you can do to prevent the flooding, and Winnipeg certainly is a case study of what maybe Grand Rapids should have done. And here's just an example of the satellite image showing the blockage and the diversion along here. So floodway channel diversion canals are really effective ways of trying to protect vulnerable areas. Now, there are actually several things that made the flooding bad. Part of it was spring thaw combined with a big rain. The other, ice jams. Again, it's something we don't see here, but what happens with an ice jam, as the water rises in a frozen river, the ice breaks up. And then that ice begins to move downstream until such time as it gets jammed, usually on some kind of a river constriction or a river turn. That jam causes literally a temporary lake to form. So you've got a flooding associated with the backwater effects of the jammed ice until it unjams, and then you have this sudden release of yet more water. So you exacerbate both downstream flooding and upstream flooding associated with these ice jams. So it's a major problem in northern rivers. The other thing is, this whole area is built on an old lake, or better said, a glacial lake. And so the topography is absolutely flat. And to make it even worse, there is a significant decrease in gradient downstream. Well, of course, there always is to a certain extent, but the decreasing gradient means it slows down. And we know that as it slows down, the water can pile up. Okay? If we look at a physiographic map, there's some interesting areas right along in here. This is up in Minnesota, North Dakota, where there's this tongue-shaped plain. It's just absolutely smooth. And what that is is an old tongue of a glacial scour that was then filled with lake deposits as the glaciers retreated to the north. And in fact, here was the area that was flooded, and here was the lake that formed. And as the continental ice retreated back to here, the land was depressed because of isostatic loading of the ice. And so as the ice was melting, where was it going? It was being trapped in this lake. And of course, the rivers were flowing into the low area as well. So you have this very wide lake in which lacustrine deposits were formed to form this Lake Agassiz. And this is called a proglacial lake. And they're very common on the margins and these moats, if you like, of retreating glaciers, particularly continental scale glaciers. And this is a map of Canada showing the extent of those old lake deposits. So we only have, this is us, you are here in the U.S., we don't have many areas like that. It's all over Canada. Okay? And what it means is that Fargo and Moorhead, which is right across the river, have just kind of spread out. And when you look at the deposits, well, here's the glacial deposits filling old valleys. Then here are those lake deposits and a little bit of river deposits. But the story is it's just flat. And so once the Red River overtops its banks, it goes on forever. Okay. So here's the hydrograph. And again, here's 5 days. So it's not a flash flood. There were evacuations. But there was a very rapid rise in the stage. Okay. Now, there is a lesson to be learned with this particular flood about understanding predictions. Okay. Here, the river crested 5 feet higher than had been predicted a week before. The problem is how hydrologists, engineers, scientists describe events and how planners interpret those events. The Forecast Center said that the Red River would reach 47.5 feet based on one assumption and 49 based on the other. But both of those predictions had an uncertainty of about 10%. So think plus or minus 10%. That's plus or minus 5 feet. Okay. The community leaders thought that 49, therefore, had to be the highest they dealt for. It could be 47.5, it could be 49, ignoring the uncertainty. Okay? So, as a result, their response, to a large extent, was to make sure that the sandbags were that high and that those were the areas. Okay. Well, they were wrong. And again, if you cannot communicate the information necessary to make sound judgments with respect to the public safety, then the whole system breaks down. That becomes the weak link in the chain. After this flood, they spent, not a surprise, hundreds of millions of dollars to build flood walls, levees, pumps, diversion canals, etc., many of which were mimicking the Winnipeg example. Now that was, here we are, Grand Forks, 1997, 40 feet. Here we are, 2009 at Fargo, 40 feet. Okay. This 2009 flood was even higher in Fargo than in the 97 flood. Okay. Then there was a 2011 flood. In fact, when you look at the flooding between 97 and 2011, there's been 4 floods that were about that high, all of which were higher than the historic flood. The good news is much of the preparation that resulted from the 1997 flood resulted in far less damage in subsequent floods. So they learned their lesson. Let's see. I'll just skip this. Again, even 2013, they had some big floods. CBS says they're really exhausted from multiple floods. And there's no question but that this has been a bad series of decades for the Red River of the North. Okay? And as it says, temporary levees prevented major damage, but there's a big change in the river. 4 floods in 5 years. Okay? Look at these flood periods. Okay? We're looking at some major changes from here to here. Something's going on. Depending on how you would extrapolate numbers, are we looking at a 500-year flood here? Is this the 100-year flood? Is this the 50-year flood? This is part of the problem. Remember when we had that big flood in Rapid City? First thought, it's a 500-year flood. Got more information, well, it's a 200-year flood. Now we're beginning to look at the fact that climate change is increasing the probability or likelihood of these floods occurring. So what we thought was a 500-year flood probably isn't. Okay. There's also the seasonality. When you look at floods, if you wanted to make a prediction of what is the recurrence interval of this type of flood for the Red River, what you would not do is necessarily look at the biggest flood every year. Because if you look at this particular graph, this is the water year from about 1905 to 2010, and this is the day of the year. Okay. Now it turns out water years are kind of like fiscal years. They start October 1. And the reason they do that is because the rainy season typically goes through the calendar year. So they try to break it at a time where it's more likely to package events. And that's what's happened here. Notice that between about 150 and 190, that's when you get a series of big floods. And then you get another series over here. Well, this is March, April. And of course, this is ice breaks, snow melt, floods. This is June, July. These are summer floods that are associated with convective storms. So if you were going to do a flood frequency analysis, you'd look at these separate from these. And you would then combine them. But you cannot look at the probability of ice break or ice melt and mix it with the probability of summer rains. The other thing, though, is look at the size of these diamonds. The size is proportional to the discharge. So what we're looking at is the relative size of the big floods as we're continuing to the present. And so there's no question that we're looking at a long-term change resulting in the increase of flooding. It's shown here, the blue are higher floods. These are lower floods. So when we go from green to red to green here, that's the Dust Bowl droughts. Okay, this is the 1930s when we had so much loss due to lack of rainfall in much of the central U.S. But look at the increasing blue. Okay, so this story is suggesting, as we know from other areas, that our whole concept of flood frequency analysis is biased towards the assumption that nothing has changed, and it's quite clear that something has. Okay. Here's our stream flow data. It's actually out of date. There were some paleo floods that were pretty big. Okay. But again, now we're looking at flood rings, historical records, gauges. now we're trying to look at some kind of a history of flooding going back 400 years. Okay. And that's important. But the problem is, we know that over 50 years there's been significant change in climate. So therefore, to think that there's been no change in 400 years is an extrapolation. So you've got to be even more careful with the information you get from these historical events and using them to extrapolate for future events. Okay. Yeah, I'm skip that. Yeah, again, these are some outliers, and remember, an outlier is a point on a flood frequency diagram that plots above where you would predict it. Now, in this particular case, that flood is based on 30 years of record. So if you remember the recurrence interval formula, n plus 1 divided by m, if it's 1, n is 30, that's the 31-year flood. That's how you plot it. But the suspicion is maybe it belongs over there. Maybe in the last 30 years, we had the 100-year flood. And that's what it would look like. Okay. This is trying to work with some of those outliers and bringing them in to try to figure out what the actual recurrence interval is. And again, we're probably looking at a couple of 100-year floods for some of them. But look at this. This is 97, and after 97, that 97 flood that we thought was the 250-year flood, we've had 3 more that size or bigger. Okay. So beware the temptation of putting too much faith in the probability of flooding, which is a sad statement because it's the best we've got. Now, having said that, these are based on floods. And so, as I hope you'll recall, a lot of our predictions now are based on rain. And rain is still changing, but the advantage of making your flood prediction based on rainfall is that it eliminates a lot of the impact of urbanization. So you can take into account urbanization because urbanization just doesn't affect, changes in land use don't affect rainfall to the same extent as it does runoff. Okay. Okay, well, let's go closer to home. Tropical Storm Allison, 40 inches in 5 days. And again, recurrence intervals are estimated greater than 500 years. 22 killed, 41 nationwide. Damage was $5 billion and 73,000 homes were destroyed. This was the greatest economic disaster due to river flooding in U.S. history. This is when we saw I-10 become a detention pond. And if we look at the map of rainfall, right in here, we're looking at over 35 inches. Now, we can determine the recurrence interval of rainfall just like we can runoff. And so we have these tables that look at how much it rained each year for different time intervals. And so if we look at this particular time period, we can actually calculate what that translates into with respect to rainfall frequency. Everything in the light blue is greater than 100-year rain. A little darker, greater than 500, and this, it's off the charts. It's, I don't know, a 1,000-year event. Okay. Again, this is using the idea we're going to extrapolate based on these records. Okay, 73,000 residences. The damage, and take a look. The red is where there was flooding due to overbank flow. And of course, that's really all we were talking about when I talked about floodplain delineation and floodplain zonation. But look at how much of the area was what we call overland flooding. It's sometimes called urban flooding, where literally it just rained so much that the water backed up into your house, from your backyard, from the street, but not from Brays Bayou. Okay, so this was one of those lessons learned, that there can be a lot of flood damage outside the floodplain. Okay. Now, what that meant was we needed to decide, is this a problem with the floodplain delineation or what? Well, once we've decided that most flooding can occur outside the 100-year flood, much rather, it puts the focus on spreading the word that people should have floodplain insurance even if they're not in the floodplain. So that was the first lesson. The second thing is, there was a concern that maybe the old floodplain maps weren't correct, and so or outdated and were incorrect. And so we got LIDAR coverage of the entire Harris County. And remember, LIDAR is that airborne laser system that allows you to map the topography to literally a few centimeters. And that allowed us a much better topographic view. And of course, you need to have a detailed topographic database in order to predict the aerial extent of flooding. It also suggested that, buyouts make sense. Maybe there are some areas that with so much recurrent flooding, we should just buy it out rather than to continue to pay more and more insurance. Oh yeah, and it wasn't even a hurricane. You don't need a hurricane to have catastrophic rain in the coastal region. And lastly, you may recall that the Med Center had their pumps and generators in the basement, and what floods first? The basement. Don't do that. The Fukushima meltdowns were another example of don't put your pumps in the basement and your electrical generators. Okay. The reality is we've got a lot of property within the 100-year floodplains. And about 10% of households are in what are called special flood hazard areas. That could be coastal flooding, it could be river flooding. Okay. There was a house in Houston, flooded 16 times in 6 years, and they collected $800,000 for a house valued at $115,000. This is when the idea, we need to stop this silliness. And so the floodplain insurance program basically developed a rationale, 3 strikes and you're out. We're not going to, we'll buy the house, but we're not going to continue to allow you to insure the house with subsidized insurance. In fact, in yesterday's paper, literally yesterday's paper, there was the beginning of a series of articles I would encourage you to read on flooding. And in Harris County, we've got 9,700 properties with what they call repetitive losses. That means at least two or more losses with claims of greater than $1,000 in the last 10 years. 1,968 had severe repetitive losses. These were greater than 5,000, 4 times or more, or 2 claims, each of which was more than the house was worth. So clearly this has to change. And the extent to which it's changing by a change in the rates of the floodplain insurance or flood insurance, that's one of the things that's happening. We're seeing more and more focus towards higher rates of insurance for those in the highest risk. The second is you'll see more and more buyouts because one of the things that's quite clear is that it makes no sense at all, and it's to cover these repetitive losses. This particular map is actually the same as one you saw earlier. These red dots, here's Houston, you are about here, are the buildings that were destroyed in Tropical Storm Allison. What you're looking at here, these are the floodplains. Now, the darker blue is the 100-year flood, or 1%. The lighter blue is the 500 or 0.2%. But now we've got two more floods. We've got the 2016 tax day flood in yellow and the 2015 Memorial Day flood in orange. And so we see there are large areas, both inside and out of the floodplain, that were damaged in these two floods. And these I'm quite sure you remember. Let's look at the tax day flood, 2016. We got over 17 inches of rain in 24 hours in some cases. When you take that rainfall and extrapolate it to a probability, just as we did earlier with the Tropical Storm Allison, we have some areas where it's a 1,000-year rain. And therefore the flood was in part a 1,000-year flood. This is a 1,000-year, 500 to 1,000, 100 to 500, 50 to 100, 10 to 50. So at least based on our records, this is an extraordinary rainfall. Now notice, it's inches per some unit time. Okay. Here, this is actually the probability of a 12-hour rain having whatever the rainfall was at that point. The Memorial Day flooding, this is a little different only because I don't have the probability, but it got 2 inches, 4, 6, up to 14 inches. Okay. So together, these floods killed 16 people and caused $1 billion worth of damage. Okay. So we're getting a lot of big floods, and basically this is becoming the new normal for Houston. And so what we do about these floods is really a pretty critical question. Now, one of the things I want to point out is that when you look at the flooding in the Harris County area, you have to think about drainage basins. So, for example, if we look at Buffalo Bayou actually has a drainage basin that's cut off like this. And the reason is that the upper parts of what used to be the Buffalo Bayou drainage area are now two reservoirs, two earthen reservoirs, Barker Reservoir and Addicks Reservoir. And these are the dams that protect it. Okay? Now, there's another area of interest, and that's Cypress Creek. Cypress Creek comes along here. It actually goes beyond Harris County, but that is in the northern part of Harris County, and that's one of the areas where we have a lot of new growth. Okay, so I want to focus on what's going on right in here. Okay, these are the major rivers. Again, this is the drainage area for Buffalo Bayou minus the areas for Addicks Dam, and this is the drainage for Cypress Creek. Oh, and this is Brays Bayou for those of you that know that area. Okay. It turns out that normally we think of a watershed as being the area where waters flow in two different stream systems. And so here is the drainage divide, rather, between Addicks Reservoir watershed, which is actually the old Buffalo Bayou, and Cypress Creek. But notice how all these rivers are coming down like this, and then they take a sharp turn right like this. Well, it turns out during big floods, a lot of water actually spills over from Cypress Creek into the Addicks Reservoir. Okay? And this is called the Cypress Creek overflow. And it spills into Addicks Dam and, to a lesser extent, Barker Dam. Almost all that overflow goes into Addicks Dam, okay? Addicks Reservoir, right here, okay? This is what the floodplain looks like, and it illustrates that when that water comes down and ponds up over here, much of it overflows the drainage divide. And it flows down these three streams to start filling Addicks Dam. Okay. So even though the rainfall was preferentially in the Cypress Creek watershed, Cypress Creek shares a lot of that water with the Addicks Reservoir. And this is actually a map of the 100-year overflow coming from Cypress Creek. And it turns out it's not real deep, typically 2 feet or less, but it covers a huge area. Now, what this hydrograph is the hydrograph. Let's take the dashed line. Okay, this is the 1% event, the 100-year event upstream of that overflow area. And this is the area downstream of the overflow. Okay, so if you're on Cypress Creek, if you're upstream of the overflow, you're getting this much water. If you're downstream, you're getting this much water. So the good news for Cypress Creek is that that Addicks Reservoir is acting like a big diversion pond or detention pond for Cypress Creek. In fact, 83% of the upstream flow goes into the Addicks Reservoir. Okay, that would be good if it wasn't for the fact that there's a lot of development upstream of the Addicks Reservoir within the Addicks watershed. And so these are areas which are beginning to be flooded. And had I pointed it out, you see that much of the damage, much of the flooded homes in these floods, they're not in the Addicks floodplain, but they're flooded by the overflow. Now, what this line up at the top shows is the amount of water that's coming into Addicks Dam over a 5-year moving average from about 1975 to 2012. We're getting more and more water coming into it every year. And the interpretation, because if you look at annual rainfall at least, we're not getting any more annual rainfall, is that increase is due to urbanization in the Cypress Creek drainage area. Okay, I'm a little concerned about the interpretation here because even though average annual rainfall might not be changing too much, we do know that periods of intense rain is increasing. So I'm not completely sure if that's a valid comparison, but it's pretty clear that we're seeing long-term increases in water coming out of the Cypress Creek area. Now, this is the Cypress Creek watershed, and this is the Addicks overflow. Yellow is residential. Look at how much urbanization there is here. All of that is contributing to increased volume of water coming into the reservoir. And same thing up here in the Cypress Creek. But Cypress Creek, there's one advantage. The upstream portion here isn't yet completely urbanized, very much unlike the area immediately above Addicks Reservoir. So let's look at where the growth is. Land that was developed between 2001 and 2010 is in pink. Okay, and it should come as no surprise of you that know Houston is that we're building on the northwest fringe. Now, we could also look around Sugar Land and Richmond and we'd see a similar fringe. So we've seen an increase in impervious surface of 25% in about a 15-year period. That's a huge increase in impervious surface. And so that's a huge increase in water that can't soak into the ground and instead is diverted for flooding. Now, it turns out a lot of that development, particularly in the west, is in what is referred to as the Katy Prairie. And the Katy Prairie is a large flatland area that is characterized by a lot of native grasses, major bird habitat, and we're losing it at a pretty significant rate. Yeah, we had these patches left. Notice how there's little patches here and here. But basically, the contiguous parts of the Katy Prairie aren't many, and they are being threatened quite clearly by this moving wave of urbanization, because much of the urbanization in pink was the Katy Prairie, and it's now the Katy subdivision. Okay. So is there any reason to be concerned other than either aesthetically or maybe ecologically? Well, look at what the prairie grass does with respect to root structure. Turf grass has a root structure about like this. Prairie vegetation sends out roots that can go down 14 feet. And what that does is it breaks up the soil and makes it more permeable. It loosens the soil. And so the presence of the prairie vegetation basically takes what otherwise would be relatively impermeable soil and helps to make it more permeable. Okay. Now, these are quotes that you don't have, but I think it's easy to understand. There are many studies now that suggest native prairie plants facilitate the absorption of a large amount of water and therefore reduce the amount of runoff. Okay. Now, one of the ways we could actually quantify that is to go back to the soil conservation curve number. You may recall that the curve number ranged from 100, which meant completely impervious, 100% runoff, to, I don't know, 20 or 30, a lot of infiltration. The area of development, or when we develop an area, the curve number is about 85. And a large amount of runoff. One study that was done for the Texas Water Development Board suggested that a restored prairie would have a curve number of about 60. Now, to translate that, it says 1 acre of prairie increases the infiltration capacity by 3.5 inches in a 100-year flood. And that is the equivalent of 2 acres of a single-family dwelling or 1 acre of a commercial retail establishment. So in terms of the hydrologic value of the Katy Prairie, it is to reduce volume of runoff. And so you lose the prairie and gain a subdivision, you're going to see a tremendous increase in runoff. Okay. This is using a slightly different technique, but it says that single-family subdivision with an impervious surface of 50% is going to increase the runoff for a 100-year event by about almost 2 inches. And for a commercial site, because it's 90% impervious, it's going to increase it by over 3 inches. So every time we think about what is happening in these areas, think of these numbers. Now, one option is not to build. Another option is, well, if you're going to increase this by 3 inches, you need to, as part of your plan, build a hole that will hold back 3 inches of rainfall cover over the area that you're covering. And so that is the strategy that's being used today for the most part. That if you're going to build a subdivision or if you're going to build a commercial site, you need to hold it on site with a detention pond. Okay. And how do you know how big it is? Well, by numbers like this. And so we say, okay, let's say you've got a 1 acre area, 3.5 inches over an acre. Okay. So that's what you would have to do. What that doesn't do, though, is recognize the ecological value, the environmental value of the Katy Prairie, because it's a major flyway, it's a major birdway. It also provides some increase in water quality by filtration. So it's a controversial dilemma because the relative advantage of urbanization versus preservation with respect to the Katy Prairie is one that's got a lot of strong feelings on both sides. And it turns out that even the technological concept of the prairie and the prairie grass decreases runoff is argued by some. The head of the Harris County Flood Control District says, those studies are wrong. All those academics, you need to get better experts. And so when he was asked, what better experts? He said, well, me, for example. They're all wrong. And then the other problem, in addition to just questioning, does prairie grass really help to reduce the runoff, is are we building those detention ponds? Because right now the rules are we're supposed to. And there's been ample studies that show, well, the problem is the subdivisions, or rather the builders are not building the detention ponds. And that is in part because they're not doing it, they're not being forced to do it, and in other cases they're providing the money to a governmental agency that says, oh, we'll take care of it, we'll build a bigger one, but they don't do it. And again, the head of the Harris County Flood Control District says, oh yeah, they are. They're all doing it. So there's just a tremendous amount of politics going on right now with respect to how to deal with this reality, this new normal of increased flooding in the Houston area. And it's mimicked by problems all over the U.S. And it's aggravated by problems all over the U.S. and the world reflecting global climate change and causing changes in the frequency and magnitude of floods and decreasing our ability to make accurate predictions about how frequently these events will occur. Let me see. Okay. All right, so what are we going to do about it? Well, I've already alluded to a few things, but let's just look at it a little more carefully. We have structural responses, and really beginning with the flooding in 1927 along the Mississippi to the present, we built things. We built dams, we built levees, we built flood walls, we channelized, and a lot of this was kind of set in motion by the Flood Control Act of 1936. Okay. But beginning in the 60s and continuing to the present, we began to see new approaches, and that is to combine management of the floodplain in terms of how the floodplain is developed along with these structures. So you've got flood insurance, natural disaster protection, and quite recently a Flood Insurance Reform Act. Okay. From about the 80s to the present, we've been increasingly focusing on what do you do after a flood. And maybe it is changing land use and buying up property. Okay. So we're relying more and more on floodplain management and hazard mitigation than the structural responses. In part because one of the thou shalt nots in structural response is thou shalt not make it worse than it was for somebody else. So you can't improve it in one area only to make it worse in another. And we're finding that structural responses tend to do that. They tend to have isolated impacts. And of course, they're very expensive. And as we'll show in a moment, sometimes they encourage us to do things we probably shouldn't do. So let's look at streams and how we're going to control it. If we want to control a stream, we need to know what are the variables that control a stream. Base level clearly is one, the level to which the water is falling. The topography is a very important one, particularly in terms of determining the amount and rate at which water flows into that stream. The climate, clearly. The stream flow, well, that's the function of topography and climate. Resistance of the underlying bedrock will say something about the erodibility of sediments and the changeability of the river plan itself. Okay. So there's a concept that was developed in the 30s, now a little later than that, in the 40s, about a graded stream. and you don't have to read this, but basically says if you look at the slope of a river, it will adjust its slope in such a way through erosion and deposition to be able to transport all the water and sediment that comes into the system out of the system. It's in equilibrium. And if you change something, like increase the water or decrease the sediment, it's out of equilibrium, and it will then try to respond. More recently, we've added a caveat that it's not just slope, but it's also the channel shape and morphology. But basically, the shape of a channel changes itself in response to these variables in order to try to reach some equilibrium. And the problem is, what we tend to do structurally changes that equilibrium. And so the river makes changes that we don't want it to do. Okay. This is just kind of a balance, but it's a good visual that says that degradation or erosion, aggradation or deposition, depends on the balance of sediment supply and water supply. Okay? So, for example, if we increase the discharge, we're going to start to erode. If we decrease the discharge, it'll start to deposit. Okay. Now, if we increase the sediment supply, we'll have deposition. Decrease, we'll have erosion. Now, the decrease of water, of sediment causing erosion, okay, is actually an important concept. And I'll illustrate that with dams. Okay. And what dams do is they change the base level. The base level is the level to which the stream flows. And the ultimate base level is sea level. It could be a lake level or something else, but usually it's the sea. And if this is that equilibrium gradient, and we build a dam, then the dam becomes the new base level. So what's going to happen when we build that dam? Well, you're going to have deposition. Okay. But you have erosion downstream. And that can be a significant problem. Because the erosion downstream could widen the channel, deepen the channel. It could cause increased loss of property, of bridges, etc. Well, it erodes downstream because we decreased the sediment coming downstream from the dam, because that's what dams do. Not only traps water, it traps sediment. In fact, it traps most of the sediment, and it only temporarily traps the water. So you're going to see a shift towards erosion. Okay? And one of the ways of thinking about it is think about the fact that the water that's released here is sediment depleted. And sediment depleted water has a certain amount of energy that needs to be dissipated. That's that slope of the energy curve we talked about. How does it do that? Well, it turns out it does it by erosion to get sediment into the system. It is as if the river needs to transport a certain amount of sediment to be in equilibrium with this system. Now, it's a bit anthropomorphic, and I don't want to imply that, but if you decrease the sediment supply, you will increase the erosive ability of water. Okay. Now, there's other problems. Deposition upstream, well, first of all, we flooded an area, so you've lost that area. But now we've got increased deposition. We've got increased flooding upstream. There's a variety of things, maybe water. Let's look at the Glen Canyon. Think about where water comes out of a dam. It comes out of the bottom, typically. That's cold water because the water is very deep. It's not being warmed, unlike the water in the river, which is relatively warm. So we change the temperature of the water downstream. by building a dam. And that means you completely change the nature of the flora and fauna. Different kinds of fish, certain kinds of fish won't live there anymore. And so that is one of the changes that you get with dams. Now, another problem, though, is you eliminate floods. And you think, well, duh, that's the whole point. Actually, it's not the whole point of dams. Dams are built for different reasons. But you do eliminate floods. And so here we see downstream from the Glen Canyon Dam, which is on the Colorado River, we see an artificial flood being created. The reason for that was that when you look at after the building of the Glen Canyon Dam, you began to erode the Point Bar deposits. Now, this is in the Grand Canyon National Park, so you might argue not a big deal, but those little sandy bars at the base of that canyon are a unique ecological niche, and they're also the place where people camp when they're going down. And they were being eroded. Okay. Well, it turns out that the reason they were being eroded is because with the decrease in water, or rather with sediment, and decrease in discharge, what sediment was there tended to pond in the river and not move up onto the point bars, because the point bars are basically flood deposits. And so it just gradually got eroded. Well, it turns out that after they did this deliberate flood, it eroded and deposited. So this was the amount of erosion, amount of deposition that occurred after the flood. So by having an artificial flood, we were actually able to get the sediment back into the bars where they belong, okay, or at least where we want them to be. Okay. So now we are trying to mimic nature by creating artificial floods. It turns out certain types of fish they lay eggs, but they need to have gravel moved in order to have those eggs exposed and hatch. And so without those floods, the fish eggs weren't hatching. With the dams, the fish couldn't migrate upstream. And so what we're finding is, in many areas, both in the Pacific and Atlantic, we are removing many dams. And we're removing them because there's a lot of things, and you don't have to look at all of these, but read it in your notes. There's a lot of things that fish can't do if there's a dam. And it's not limited to fish. Okay. But we've completely changed the ecological niche when you build a dam. And many of these dams, I should add, were built for small hydroelectric dams associated with mills or something, particularly in the Atlantic region, Northeast, where they really weren't serving much of a function anyway. And some of them in areas of high sediment yield were filling up because that sediment load was so great. So the cost benefit for removing some of the dams was not as great as you think. And of course, the poster child for dams and unintended consequences was the building of the Aswan Dam. The Aswan Dam with Lake Nasser was essentially blocked off the sediment in the Nile River. And we've known since Herodotus that the Nile is the gift, or rather the delta is the gift of the Nile. And we've got the Nilometer, which is literally a gauging station that shows the elevation of the flood every year for over 1,000 years. So this has been an area that we know pretty well. And one of the things that happens, of course, is that that area would flood, not catastrophically, but flood over wide areas, and with it brought nutrients as part of the sediment load, organic material. And so the farmers would basically plant every year based on that flooding. In addition, in the coastal regions, these were major areas of coastal hatcheries, etc., for both fish and shrimp and other things, crustaceans as well. Build the dam, what happens to the sediment? What happens to the floods? You no longer had the water overflooding and you no longer had the sediments. So now you need to bring in artificial fertilizer because you no longer have the natural fertilizer. In addition, we begin to see subsidence. In addition, there's not sediment and nutrients that are reaching the coast. So the fisheries now are going defunct. And so ripple effect on ripple effect on ripple effect with these big dams. And that's one of the reasons why we're not building them anymore in the U.S. China is. China's rationale for building big dams is because they have so much of their energy demand locked up in coal. And the air quality issues are so bad in China that the trade-off between the ecological losses of building a dam for hydroelectric power and coal-fired electrical plants, the rivers are going to lose on that one because the air quality issues are greater than that. Okay, so let's just real quickly summarize. Dams can be used for flood control, power, water supply, recreation, even though realizing some of these are mutually exclusive. The cons are a variety of things here, and that's one of the things you might think about on a study guide question, probably the pros and cons of dams. Okay, and we will finish up other types of flood control issues and then hopefully deal with erosion next time. Yeah, just 1 minute.